this is a diagrammatic, this is the diagram representing the immiscible liquid. Listen carefully, please. So here we have two liquids, kerosene, for example, and water, or either benzene and water, right? So what happens? We say that because these are, we mix two solvents, there's a tendency of forming vapor pressure above these immiscible liquids, right? So the question is, the total vapor pressure of immiscible liquids will be formed by contributions of kerosene itself, or by water itself, or by both kerosene and water. So the answer is, we say that for the immiscible liquids, each liquid, not only one liquid, each liquid, if you have immiscible liquids of the two liquids, then each liquid will contribute a vapor pressure regardless of the presence of the other liquid. So what does it mean? The kerosene will contribute the vapor pressure in the total vapor pressure of immiscible liquids regardless of the presence of water, right? And then water will contribute some percentage of vapor pressure of immiscible liquids regardless of the presence of kerosene. Okay? So that's the very important point for you to note and to take into consideration. So again, so now let us think in details about this vapor pressure of immiscible liquids to say that according to the Dalton's law, according to the Dalton's law of partial pressure, law of partial vapor pressure. Okay, so it stated that, okay, do you remember the Dalton law of partial pressure? We learned it in gaseous state. Okay, so it stated that the total pressure, total vapor pressure, right? Total vapor pressure exerted by the mixture, such as immiscible mixture, is the sum of what? So this is the sum of the equilibrium vapor pressure. Sum of the equilibrium vapor pressure. Equilibrium vapor pressure. Okay, equilibrium vapor pressures. This is according to Dalton's law of vapor pressure. So we learnt it in gaseous state, but we have to recall it in the mixture of the liquids, especially for the immiscible liquids. So how does it state? We say that according to Dalton's vapor pressure, he stated that the total vapor pressure of the mixture, of the non-reacting mixture, we say that of the non-reacting mixture exerted by the mixture is equal to the sum of the equilibrium vapor pressures of individual solvent, right? So then we say that in order to have mathematical expressions for the Dalton's law, we say that suppose that solvent A is mixed with solvent B, right, to form vapor pressure. To form immiscible liquid. So then we say that Dalton's law, or Dalton's equation, Dalton's equation will be in this form. The total pressure is equal to partial pressure of solvent A plus partial pressure of solvent B. So remember that this is total pressure, whereby this is total pressure, and then this is partial pressure for this pure solvent A, and this is the partial pressure for the pure solvent B, right? So Dalton law is still applicable. So you say that the partial pressure of A, this is equal to vapor pressure of pure solvent A, and then you have this guy B, this is equal to vapor pressure of pure solvent B. 10. So this is Dalton law of vapor pressure, very important law in this perspective. So it's very important law in this perspective. So now let us go to the second applications of steam distillations, where we say that we use steam distillation to calculate the weight, the molecular weight of organic compounds or of the liquids by the steam distillation process. So that's the second concept that we are going to learn. We have covered about vapor pressure. You know the vapor pressure that will be there will be coming back to that. We combine these concepts with the second concept, and where we are heading to steam distillation. Say with me, steam distillation, that we learned in lecture 1. Steam distillation equation. Steam distillation equation. Or in the other way, we say that the formula, the derivation of the formula of finding the molecular weight of organic solvent, or most viscosity of the liquid. Organic solvent of immiscible liquid. It's a kind of long title, but don't worry, you have to understand about that. So we are going to the second concept before we go for the problem solving. Derivations of the formula of finding molecular weight of organic solvent or liquid of immiscible liquid by using the steam distillation method. By using steam distillation. Steam distillation. So now let us go to business. So we want to derive. We'll be following some steps on deriving this formula. And even yourself, you should not cram it, but you have to know where can you start on your derivations to derive the desired formula. So we say that the first step on this derivation, we say that consider a beaker with solvent A and solvent B. B forming immiscible liquid. So this is the diagram. Okay, so suppose that this is solvent A, which is less denser than solvent B. It's a volatile, we call it a volatile solvent. And this is solvent B. So suppose that this is solvent A, solvent B, and this is solvent A. So if you say that this solvent A and solvent B, this is the separating layer. Okay. So our intentions, we want to do this derivation and then enjoy the derivations and having some two issues which are very important. So we go for the second state. The second state, remember that the solvent A has a tendency of forming vapor pressure above it. And solvent B also has a tendency of forming a vapor pressure above it, right?
Yeah.
So because it's vapor pressure, then we say that the second step, we say that recall the concept of what? The concept of Dalton's law, right? Dalton's law of vapor pressure. Okay? So according to Dalton's law,